The Jurassic is the middle period of the Mesozoic era, and every period from here on out in Earth's history is going to be somewhat packed with geological events and different life forms. Geology exposed in Zion National Park of southwestern Utah shows the Glen Canyon group and rocks of the Navajo sandstone. This is East Temple, and that's the massive cliff-forming Navajo sandstone, which represents a coastal sand desert of the Jurassic, much like the Sahara Desert today. Life forms of this time included dinosaurs like this. That's not a tyrannosaur. You can tell mainly from the hands here. It's got a different number of fingers than a tyrannosaur, and the limbs are longer. That is an allosaur. So allosaurs are Jurassic versions of what would come later in the Mesozoic, the tyrannosaurs. So those are major league bipedal predators of the Jurassic. The Jurassic period spans the range in age of 201 to 145. Here we are on the time chart with the Jurassic following the Triassic, split into lower, middle, and upper divisions, sometimes just called early and late. People don't even identify middle. So depends. I know you really want to talk about the Kimmeridgian, but we won't be doing that today. So named for exposures in the Alps, specifically in the Jura Mountains in Switzerland. So here's Europe and the Alps. The Jura Mountains are kind of the front range there of the Alps. These are the cliffs of Croix du Van in Switzerland. Beautiful place. You can walk right up to the edge there. Magnificent landscape. Geography of the Jurassic, dominated by Pangaea and its remnants. At the beginning of the period, we see a continuation of what was going on at the end of the Triassic, the initial rift stage of Pangaea here, rifting Laurasia away from Gondwana, the southern part. So as this progresses, the seaway will mature and connect and form a very narrow seaway that we'll be able to call the North Atlantic Ocean. By the late Jurassic at about 152 or so, it'll be a narrow seaway, and Laurasia will now transform into what we know of today as North America. Notice that the southern part of the Atlantic is not formed yet. So the Atlantic didn't form all at once, it formed in stages. The Gulf of Mexico is also forming during this time. As the North Atlantic formed, so did the Gulf of Mexico. The Pacific now is out there as North America comes into its own by the end of the Jurassic. We'll start talking about the Pacific Ocean instead of Panthalassa. Notice that the Tethys Ocean here is growing in size as the subduction zones consume the Paleotethys, and it's almost entirely gone by the end of the Jurassic. And so really what's going on here is, again, Gondwana is a separate feature by the end of the Jurassic, much like it was earlier in the Paleozoic. So it's a similar layout with North America and the southern continents separate from each other. They're spreading away from each other here, but over here the subduction zone is closing this Tethys Ocean basin, and these continental blocks will be moving northward with time. So kind of pinwheeling in a counterclockwise direction there. One last thing to point out, for the first time in a while, at least since the Mississippian, we have free flow of water along the equator. So water before had to go around the huge land mass that was Pangaea. Now there is a seaway by which water can travel from the Pacific Ocean into the Atlantic. So that's a definite change. Let's look at the paleoglobes for the Jurassic. Here are the early Jurassic interpretations at about 200 million years or so. So we can see Pangaea is still intact. Laurasia is still connected with Gondwana. You can start to barely make out the outline of North America. You can see South America to some degree as well. That rifting progressing from the east is not yet complete. Notice in the ocean basin out here are various arcs and other tectonic terrains that are moving slowly eastward, brought that way because of subduction zones. In the other hemisphere, it's mainly the Tethys. The Paleotethys is pretty much destroyed or just about there, and this is the mid-ocean ridge here that's creating the Tethys Ocean. As we move forward in time to the middle Jurassic at about 170, notice the rifting has progressed almost through to the west side here. Inland seas have spilled onto the continent. Some of those terrains have actually collided with western part of North America. Notice that there's just the first trace of rifting of the southern continents. So the northern Atlantic basin is forming first, long before the southern Atlantic. On the other side of the globe, there's still the Tethys. And then finally in the late Jurassic at about 150, the culmination of rifting and the first free flow of water from the western hemisphere and the now Pacific Ocean east to west across to the Tethys. So it's been since the Mississippian period that it's been possible for water to flow more or less along the equator freely from east to west. It's always had this big landmass in the way called Pangaea. So this more or less separates off the northern continents, and now North America is born. The rifting of the southern continents is progressing, but still not nearly complete. The Tethys Ocean is narrowing somewhat, and a lot of tectonic activity on its northern border. So let's go back and look at this sequence. Let's just look over here at the rifting from early to middle to late. Early, middle to late. Notice the rifting in the south. Early Jurassic, it's barely there. By late Jurassic, it's starting to form the outline of South America and West Africa. So look at these terrains out here, progressively getting closer and sometimes colliding with North America. Early Jurassic, middle, late. Finally, Tethys, which stays a significant ocean basin the whole time. Just look at it. And the major changes over here on the southern margin of this northern landmass here of Eurasia. Okay, I'm going to do it. I'm going to call it North America now. Even though it's not quite rifted away from Gondwana, not completely, at least by the early Jurassic. Sometime later in the Jurassic, the complete rifting will occur, but let's just call this North America, what was once Laurasia, and before that Euramerica, and before that Laurentia. Okay, so here's the rifting in the rift basins with their evaporites and continental sediments. The west coast, Arizona, is over here, giant sand sea occupying much of Utah and Arizona. Active continental margin over here with various terrains being accreted onto the west coast. Notice no Alaska here at the time. And there's more coming off to the west. That's early Jurassic, about 195. This is a little bit later, still during the early Jurassic, about 180. Notice this material has moved a little bit farther to the east now, a little bit closer. The sand sea has enlarged, and the rifting has progressed that it's almost complete between east and west. Middle Jurassic, for the first time, a seaway has formed between the Western Ocean and the Eastern Ocean. The now Pacific Ocean in the west, the Tethys east. Just above the equator, notice this broad inland sea. It's a big four-one basin sea, still have the sand deserts. And then in the late Jurassic, the maturation of this rift, it's widening, it's still a seaway connecting the Pacific with the Tethys, Foreland Basin sea deserts, these island arc and other terrains being added onto the west coast, like tectonic waves crashing on the shores of North America. So early Jurassic, let's look at the margin over here. Okay, so these terrains, when they come into contact with North America, will result in orogenies. So from early Jurassic, middle to late. The development of the Foreland Basin seas as these orogenies take place. Form, grow very large in the middle Jurassic, and then start draining off by the end. And finally, let's look at the separation of North America with Gondwana here. Early Jurassic, middle, and late. Well, let's look more closely at western North America. During the Jurassic, at least in the early Jurassic, dominantly continental sedimentation, a large sand sea occupied much of the region. Large sand seas are also called ergs, E-R-G. The Sahara has different ergs, and major deserts of the world have sandy components we call ergs. And this was at least one or more ergs put together to form a giant sea of sand. Still had a lot of terrain accretion going on in the northern part of the margin, folding and thrusting and highlands developing. In the south, we have this new east dipping subduction zone with oceanic crust going underneath North America now, and that's going to form a continental volcanic arc. So not just island arcs from up here, but now the arc volcanoes are forming on the continental plate. That's like the Andes or the Cascades of today. So a lot of explosive eruptions occurring down here in the southwest margin of North America. Huge volcanic mountain range, behind which is a sea of sand, an inland dune sea. This area is dominated by the Nevadan highlands off on the western margin. These are mostly tectonic in origin. This is the area of the Nevadan highlands, and these result from the accretion of island arc terrains and others onto the western part of North America. So folds, thrusts, that kind of thing. This shows the line of mountains we call the Nevadan highlands, and as a Foreland Basin develops, in comes the sea. And this sea actually has a name. It's called the Sundance Sea. In the middle part of the Jurassic, it fills up this lowland. Eventually, it will drain off by the end. Here we can see the remnants. If you remember the progression we showed, the sea was bigger and towards the middle and then drained off by the end, leaving a swampy, marshy environment behind. So mountains here on the west, big Foreland Basin to the east of it. And so this whole area was dominated by streams and floodplains, swamps, huge sand desert down here. This shows the Luan Salt as that rifting was taking place. So a number of different environments here east of the Nevadan highlands. Okay, the major feature is the Sundance Sea, of course. So by the end of the Jurassic now, we would start to see not only this Nevadan highlands forming these tectonic mountains rising in the east, but also a line of volcanoes down here in Arizona and farther south, which represents that continental arc I was talking about. So as alluded to with our geographic discussion, the tectonics during the Jurassic dominated by the rifting of Pangaea. It's progressing from east to west over time. Again, looking at this tectonic diagram, the red line is the area of rifting. In the early Jurassic, it is partially progressed into Pangaea, but by the end of the Jurassic, it would complete the job and make it all the way to the west side. And the intervening area between North America and the southern continents is the new North Atlantic Seaway. It goes from initial rift basins and to a narrow seaway by the end of the Jurassic. There are all sorts of other tectonics going on too. The crashing in of these island arcs and other fragments into the southern end of Eurasia over here is causing various orogenies. On the west side of North America, we're going to see another orogeny here as well, as some of these terrains start to collide and accrete onto North America. Well, if you look at the North Atlantic, we have progressed. By the end of the Jurassic, we actually have a seaway. So in the Triassic and early Jurassic, rifting of Pangaea, forming rift basins that become interconnected over time, eventually connecting the Tethys in the east with the Pacific in the west. A narrow seaway underlain by oceanic crust, which will only widen more and more with time into the Cretaceous and then into the Cenozoic. So this diagram shows the various tectonic elements. Here's the North Atlantic Seaway, separating now the southern continents from North America. They still call it Laurasia here, but I'm calling it North America because it's its own deal now. Globally, again, the main event is the rifting of the supercontinent, formation of the northern Atlantic Ocean, and then there's all these other kind of marginal orogenies going on, not just here in North America, but also in Eurasia as well. Well, in western North America, we have another orogeny. The Nevadan orogeny begins in the Jurassic and will last into the early part of the Cretaceous. Another subduction-related tectonic event, a lot of folding, thrust faulting, a lot of uplift. This diagram shows the nature of the collision. Here is North America and the east dipping subduction zone, subducting down underneath North America, creating continental arc activity itself, but also bringing other terrains tied to this plate closer and closer to North America. So that's kind of the general environment for not just this orogeny, but the previous Sonoman and even Antler orogeny. So you have the continental plate here, and material is being brought closer and closer and closer, in this case by a east dipping subduction zone. Lots of folding and thrusting, and even a 4-1 basin can be created. So here's another diagram of the Nevadan orogeny tectonic margin. Here is the oceanic plate, which is subducting underneath North America. As it goes down, you get melting, the melts rise, those magmas can pond and form plutonic bodies called batholiths, and they eventually may erupt to the surface to form a line of volcanoes, in this case on a continent, so that forms a continental arc, much like the Cascades of today or the Andes of today. Above the subduction zone, you get this line of volcanoes. Off towards the subduction zone itself, you can get various tectonic elements which are still exposed today. California. If you can think of this as the North American plate as a bulldozer, it's bulldozing all this oceanic sediment and even the upper part of the oceanic plate into slices and a pile of material out in front of the continent as North America moves to the left and this oceanic plate dives down to the right. A very common tectonic element called an accretionary wedge is this right here. It's all under the ocean, and it's a jumble of different sediments and volcanics called a melange, and this is specifically the Franciscan melange. The Great Valley ophiolite here is actually a slice of the upper part of the oceanic crust. So these are exposed now in California, not only in the Great Valley, but there are pieces of Franciscan melange that are in the San Francisco area. In fact, both of these are represented in the area on the north side of the Golden Gate Bridge. And that whole area has exposures of these different tectonic elements. This four-arc basin here, it's a deeper basin, marine basin, where you're getting various muds and what are called gray wackies, very fine-grained sediment deposited. That's called the Great Valley Sequence in California. The continental arc itself is forming, so that's another element to this. And the batholiths beneath those volcanoes are represented by the Sierra Nevada batholith, granitic and dioritic intrusions that were feeding these volcanoes. Today we don't see the volcanoes anymore, but we do see the magma chambers that likely fed this continental arc. Let's talk a little bit more about how material is added on to the margin of North America. What's called terrain accretion. This diagram here is a nice simple diagram which shows how material is added on to the margin of a continental plate. This might be thick island arc material, might even be a microcontinental fragment, but it is attached to this oceanic plate which is subducting down, in this case, to the east underneath the continental plate. So with progressive subduction, that material is brought closer and closer and eventually loaded up and added to or accreted onto the continent. So this new terrain came from somewhere else, and so when we map it out, it looks like it might have different compositions of rock than the native continental rocks here. It might have different structures, different fossils, different ages. So we call these new terrains exotic terrains, or even suspect terrains, or even accretionary terrains. Those three words are all used to describe this kind of material that can be added on. So on the west coast we've seen this in stages, various terrains added on over time. And what happens with subduction of this material, when you get island arcs or continental fragments that can't be subducted, they get accreted onto the continent. That really shuts down subduction, at least for a time. The plate's still wanting to move to the right there. It can't subduct anymore because this has kind of jammed it up. So what happens is a new subduction zone tends to develop off on the seaward side of this accreted terrain. And so later in time you'll get a new subduction zone which will bring more material. In the western part of Eurasia and now North America, we've seen a number of these orogenies already. In the Paleozoic, from the end of the Devonian into the Mississippian, we saw the antler orogeny, which was a subduction-related island arc accretion orogeny. Then at the end of the Permian into the Triassic, we saw the Sonoman orogeny, island arcs and Sonomia added on. Now we're seeing another subduction-related event, the Nevadan orogeny, and between the Jurassic and now we're going to see two more. One in the Cretaceous and then one that begins in the Cretaceous and goes into the Tertiary. So 5 different subduction-related orogenies on the west coast, all adding terrain, each one adding more and more material. This is how the west coast of North America was built. Over time, piece by piece. Antler orogeny added a little, Sonoman added some more, Nevadan added some more, Sevier some more, and then finally the Laramide would form a lot of the landscapes we still see today in terms of the Rocky Mountains. Jurassic rocks. Let's first start with oceanic crust. The age of the oldest oceanic crust is about 200 million years, so earliest Jurassic. There is an older oceanic crust because it's the destiny of this kind of crust to subduct, and it gets destroyed, and we just don't have a record of it older than middle of the Mesozoic. Continental crust, we have record all the way back to the Hadean, fragments that are over 4 billion years old. But oceanic crust, not the case. Continental crust doesn't get subducted like oceanic crust does. So this is a map showing in gray all the continental areas, and then in color are the oceanic crustal areas, and the different colors are age periods. Red is where oceanic crust is forming today and is fairly young. And then the next color is orange, and that is oceanic crust that is formed over a certain amount of time, maybe 20 million years or so. You can see the symmetrical pattern because that's how mid-ocean ridges work. It's forming oceanic crust, pushing it aside, or being pulled aside by subduction zones, slab pull. This symmetrical pattern, which we first recognized in the 50s and 60s, and then interpreted that as seafloor spreading. The rocks are youngest at the mid-ocean ridge, and they get older as you move away in either direction. We can see older, older, older. This is the oldest rock of the Pacific Plate. And the eastern side, we don't see those because those have already been subducted underneath North and South America. In the Atlantic, notice here's the mid-Atlantic ridge. We see the same patterns. Here is the oldest oceanic crust in the Atlantic, Western Atlantic and Gulf of Mexico, and on the other side as well. There's some old oceanic crust in the Mediterranean still surviving. That might be actually the oldest, and there's some other small areas where there's very old oceanic crust. We now have a record of oceanic crust from Jurassic and younger. One last thing to note here is the pattern. You're probably looking at this going, well, the pattern here is similar yet different. The age zones are a lot wider in the Pacific than they are in the Atlantic. You know why that is? Right. The spreading rate of this oceanic ridge here, the East Pacific Rise, is much faster than the Mid-Atlantic ridge. So for any given period of time, say like the orange time, it's creating this much plate, versus in the Atlantic, it's forming just a thin little sliver. Okay, it's like an order of magnitude greater crust production in the Pacific than the Atlantic. Well, why is that? Right. The Pacific is rimmed by subduction zones almost around its entire boundary, and that's where the Pacific plate's going down, and as the oceanic plate goes down, it's like an anchor pulling on the rest of the plate. So the more subduction zones, the more plate going down. That's what we call slab pull. So slab pull is what drives oceanic plate movement, and there's greater plate movement in the Pacific because there's greater slab pull due to these subduction zones. Whereas in the Atlantic, the only subduction zone would be right here in the Caribbean and right here in the South Atlantic. Everything else is just passive margin. So Mid-Atlantic ridge is opening up, but there's no slab pull. So it's a much slower rate of crustal production. Well, some other Jurassic rocks of note. Just like in the northern Atlantic, we had the Central Atlantic Magmatic Province or CAMP. In the south, we had the Karoo-Farrar flood basalt. This is in South Africa and Antarctica and even into South America. These are fairly long-lived flood basalts that lasted from the beginning of the Jurassic to the end. But they really peaked, and the majority of it was focused at around 180 or 181. This is a typical outcrop of rocks related to this sequence. This is a dark diabase sill intruding into lighter colored sedimentary rocks down in Antarctica. These kind of rocks represent the initial breakup of supercontinent Pangaea and then the southern part of it, Gondwana. So we had camp in the north, now we're having this in the south. Again, as supercontinents start to rift apart, this is the progression. The heat from the mantle bows up the crust and you get various fractures in there. Decompression, melting forms this magma. It erupts onto the surface in high volume as you get the spreading. So flood basalts are commonly related to the initial phases of not just supercontinents spreading apart, but also the initiation of mantle plumes. Anyway, if we look at the map here, we can see Karoo is in South Africa. There's a province in South America, and these units extend across into Antarctica where Farrar is located. These flood basalts are not related to a mass extinction event, but they are related to some more minor extinctions we call extinction pulses. This shows the frequency of eruption of the Karoo-Ferrar, and you can see that it more or less peaked at about 181, with the majority of the eruptions occurring between about 185 and about 178. So there's a period of less than 10 million years where most of this is being erupted. These are major extinction pulses, not mass extinctions, but lesser short extinction events, and a number of them are related to this eruption. One thing that happens with flood basalts is when they erupt on a continent, called as continental flood basalts, the gases go right into the atmosphere. But sometimes these will erupt underneath oceans and gases will mix with the water instead of the atmosphere. The various gases will combine with the free oxygen, soaking up the free oxygen, and it will result in what's called an oceanic anoxic event. And we see a number of these throughout the Mesozoic. A little closer to home is the Glen Canyon group of Western North America, and this is a package of different rock formations of early Jurassic age. Glen Canyon is located where Lake Powell is today. The building of the Glen Canyon Dam created Lake Powell, which filled up what was known as Glen Canyon. So rocks of southern Utah, all the way from the southwestern corner, farther into the central part of the state, and even into Arizona, we see Glen Canyon group rocks. On the strat column here is the Glen Canyon group. There's a number of different rock formations in there. These are all fluvial and aeolian rock units, all continental. They're either stream related or wind related, and mostly sandstones and mudstones. Here's another strat column for this area. So the Triassic was the Moenkopi, and then the Chinle, and then the Jurassic Glen Canyon group right here. And it shows the Glen Canyon group's made up of a couple different formations, and each one of those formations actually has smaller members. The Wingate sandstone at the bottom. The Wingate is mostly an aeolian sandstone. There's also another member that's called the Moenavi Formation, which is more stream. So a little farther west it's Wingate, a little farther east it's Moenavi. That's overlain by floodplain deposits of the Kayenta, and that's overlain by a massive thickness of pure quartz arenite sand of the Navajo sandstone. So those are the different rock units. I'm not really going to be concerned with all the different rock names, but the Navajo sandstone is a significant unit. Major thicknesses, a lot of exposures, very distinctive cliff-forming exposures across northern Arizona and southern Utah. In Zion National Park, the upper portion of the canyon is dominated by cliffs of Navajo sandstone. Very clean, pure quartz arenite, huge crossbeds, dune after dune after dune on this inland sand sea, an erg. The Navajo sandstone, like a Sahara of the Jurassic. That's exposed at Zion National Park. A little farther east towards Lee's Ferry in Arizona are the Vermilion Cliffs. And the Navajo here is a little bit redder in color, but there are lighter portions here as well. But at the top of this cliff sequence here is Navajo, beneath it is Kayenta, and underneath that's Wingate. These are the Vermilion Cliffs over near Lee's Ferry. In fact, this area is where one of the California condor restoration areas is, up in these cliffs. Staying in the same area of south central and east central Utah is the San Rafael group. The San Rafael group is a little bit younger than the Glen Canyon group. This is Middle Jurassic. Most of the rock types are similar though. They are continental sands and muds, fluvial and aeolian in origin. And so there's a number of different rock formations of the San Rafael group. The Carmel Formation, which actually includes some carbonate, a little incursion of the sea. The major middle part of it is the Entrada Sandstone. This is a noticeable sandstone in various areas, whether it's towards Hanksville or at Moab, where Arches National Park is. Here's Delicate Arch carved into the Entrada Sandstone of the San Rafael group. Here's Devil's Garden. Okay, notice the joint pattern, all those parallel fractures. Nice massive sandstone. It fractures in a certain direction, and then weathering and erosion along those fractures produce these fins. And spring activity after that will start to eat away at a fin and form an arch. So that's Arches National Park. Beautiful terrain, the Entrada sandstone, the Curtis formations in there too, that overlies the Entrada, and then the Somerville finishes it out. So I'd have to say, just like the Navajo is the distinctive representative of the Glen Canyon group, the Entrada sandstone is that for the San Rafael group. One last Jurassic rock group to talk about from the desert southwest is the Morrison Formation. This is late Jurassic in age. Looking at the strat section for Arizona and Utah, the Morrison lies just above the San Rafael group. Okay, and there's different members of it, but it's dominantly a package of rivers and streams, lakes and swamps. So a diverse suite of continental sediments formed as that Foreland Basin, the Sundance Sea, drained off and left these wetlands behind. And these wetlands were a great location for plant and animal life. They're very dinosaur rich. In fact, the Dinosaur National Monument, western Colorado, seen here, has an abundance of various body fossils, many of them very large sauropods like this guy. So a huge array of different types of dinosaurs, from the bipedal theropods like the allosaurs to the huge sauropods like Brachiosaurus. Well, in the Jurassic, we're going to see a little bit of climate change. So it begins warm, a continuation of the Triassic, but it cools to a low point towards the end. So the cooling trend towards the end of the Jurassic. Overall climates were tropical to subtropical. Still no ice caps that we think. It just wasn't cold enough yet. We do think there was significant monsoon activity with the increased moisture. The interiors of the continents of North America and what is still Gondwana would remain arid and semi-arid. You'd still see these huge desert sand dune areas. So these would persist, but tropical and subtropical climates would increase through the Jurassic. Things would get cooler in the later part of the Jurassic, and this is mainly due to the breakup of Pangaea, which has progressed in the north and then just starting in the south. And so what that does is it allows the circulation of water, and it really mitigates the extreme climate zones that we had before. Having this greater oceanic circulation helped to change the climate. As with the Triassic, the Jurassic has climate data from rocks spread across all the different continents, and these different rock types would record different climate zones. So abundance of coal, Jurassic coal, would mean swampy environments in a climate that would support that. Evaporites, more arid environment. Tillites, more glacial. Now Jurassic life. Let's go with land vertebrates and dinosaurs, of course. So the Jurassic is a time of expansion for dinosaur species. During the Triassic, they were small and limited. They had to compete with various other early archosaurs. So ones like Coelophysis and Herrerasaurus, which were around in the Triassic, would give way to a whole range of new dinosaur types. Over 1,000 non-avian, so ones that basically couldn't fly like birds. Over 1,000 different species that we've divided into two orders based on their pelvic structure. Some have hips that are shaped like bird hips, have the same kind of structure. We call those ornithischian, so bird-like. And some which are more lizard-like, we call those saurischian. We see a radiation of the different types. We see an expansion of the size. All different types of dinosaurs were coming of age in the Jurassic. Not all of these would appear in the Jurassic. Some of these are Cretaceous forms, but we would see members of all different groups. It's interesting that the birds actually would be descendants of lizard-hipped dinosaurs. You think that they would evolve from the bird-hipped ones, but that's not how it worked. These would be the dominant land vertebrates for not only the Jurassic but for the Cretaceous. And one of the most successful higher order land animals of all time. Let's look at a few different kinds of dinosaurs. The first are called theropods, and these are the ones that are fairly agile, typically walking on two legs, bipedal, and we think they were meat eaters, so they're carnivores. Agile bipedal carnivores are theropods. Here shows Allosaurus, one of the biggest, most dangerous, baddest theropod of them all. It lived in the late Jurassic around 150, 155. It got fairly large. Notice the long arms, different from T-Rex. Very similar, the neck's a little bit different, a little longer maybe, but the arms are really what are distinctive about Allosaurus. There are also Dilophosaurus. Dilophosaurs had the bony crest in their head. Could get fairly large, but these were bipedal and they had that bony crest. These are found in the Kanta Formation and Moenavi Formation in Arizona. Another major type of dinosaur were the sauropods, and these were the large, heavy, four-footed herbivores, not bipedal but quadrupedal. There are many different types of these. They typically walked on more or less column-like legs to support their huge mass, whip-like tails, very small heads with relation to their body mass. But some of them were lower to the ground. Some of them, like Brachiosaur, would actually have a more erect neck as opposed to Diplodocus, which was more low to the ground. So sauropods were giant vacuum cleaners of the forests and the plains of the Jurassic. By the way, these are all sauropods just from the Morrison Formation. Diplodocus is one. Brachiosaurus is another. Note the difference. It's a little bit more upright here than Diplodocus. Apatosaur is this guy. Okay, Camarasaurus, there's actually one of these at the museum in Mesa. One last thing, shows a Brontosaurus. You know, that name fell out of favor. Brontosaurus, well, now it's back in favor. So if you say dinosaurs are Brontosaurus, you're okay. One last type of dinosaur includes the Ornithischia. And these are bipedal to quadrupedal herbivores. Huge diversity of different types, from the typical Dryosaurus here to Stegosaurus. So you can see the plates here. Much like the Pelycosaur of the past, these plates could be for body temperature regulation. As a defense, with blood coursing through these plates, it would possibly change their color and appear more menacing to an opponent, or it could be for mating. So there's many different, or it could be just cause. Nature just does that. So very small brain to body mass ratio here for Stegosaurus, as is the case with a lot of these dinosaurs. Note the very dangerous and scary tail. Well, another group of land vertebrates to come on the scene in the Jurassic, the mammals. In the late part of the Jurassic, we see the first true mammals evolving at about 160. And these are evolving from the mammalia forms of the Triassic. Most of those would go extinct, but class Mammalia would flourish eventually in the Cenozoic. So starting small, here is Uromia sinensis, quite possibly the first placental mammal ancestor. So they're still small. Amazing that they survived the age of dinosaurs, but they did. And so they would remain small throughout the Mesozoic, biding their time. So it was a rough time for mammals from the late Jurassic into the Cretaceous, but they only have another 94 million years and then they can rule. Just in case you didn't know which one the mammal was. Well, vertebrates were in the air as well. include the pterosaurs. So these are, again, flying reptiles. We've seen these before in the Triassic, and there's a range of different kinds. The oldest known pterodactyl is late Jurassic, about 163. That's Cryptodrachen, and it wasn't very large. This is how they probably walked around on land, somewhat awkward looking, but they got the job done. And so remember, these are their hands, their arms, and between their arms and legs was this wing membrane, much like a bat. When they were grounded, they had feet and hands, and they'd walk around like that. Another type of pterodactyl here, much smaller, and this is a little bit younger in age. And then there's Rhamphorhynchus. Rhamphorhynchus is a little bit larger, late Jurassic in age. Well, now we can finally talk about birds. In the Jurassic, we'd see the oldest known undisputed bird, late Jurassic age, and it's known as Archaeopteryx. It wasn't like our modern birds today. It probably wasn't a great flyer, but somewhere in evolution between birds and certain kinds of theropod dinosaurs. So we think this happened in the later part of the Jurassic. If we look at the phylogeny of birds, let's go back to here where we can see the reptile family tree. We see the ornithischians split off going one way and the saurischians going the other. So all these are order Saurischia. And then at some point, the theropods, allosaurs would be a part of this group, and there's some smaller forms. The tyrannosaurs are part of this theropod group, and other kinds of dinosaurs. A little farther on, we get the dromaeosaurs, and these are the raptors. And there's different types of dromaeosaurs, including Utahraptor and Deinonychus and Velociraptor. And we think they actually had feathers. So the dinosaurs starting to acquire bird-like features. And so Archaeopteryx is the next stage of that. We actually think it's a bird and not a dinosaur. So the evolution of class Aves, which is the birds, and now we see the descendants of Archaeopteryx today. These are avian theropods, but they're not reptiles, they are different class. Okay, so class Reptilia here would evolve into another class, class Aves. So Archaeopteryx spans that boundary between dromaeosaurs and birds. Let's take one last look at birds. Okay, and they're essentially avian dinosaurs, flying dinosaurs. Okay, let's see why we say that. Here we have a phylogenetic tree starting with the amniotes, and they would branch into two types of reptiles in this case, the synapsids and eventually the diapsids. Okay, the synapsids are mammal-like reptiles, would spawn the pelycosaurs, Dimetrodon, and then therapsids, all mammal-like reptiles, mammalia forms, and finally the mammals. On the other side, the diapsids here would branch into a number of different forms, like turtles and lizards and snakes. But the archosaurs here had different forms, the extinct archosaurs like Postosuchus and such, but also the dinosaurs. Some archosaurs would evolve into flying varieties, the pterosaurs, and some into land varieties, or dinosaurs. So some were avian, and some were non-avian. And of those dinosaurs, some developed bird-like hips and lizard-like hips. They would go extinct. They were non-avian. They couldn't fly. The lizard hip ones would develop into two major groups, the big lumbering sauropods. They certainly couldn't fly. They were non-avian. And these theropods were allosaurs and tyrannosaurs, and they were non-avian as well. They would eventually go extinct. As would the raptors, like the dromaeosaurs. Those were all theropods that would go extinct. However, from that lineage would come the birds. So this is actually the only avian member of this whole group. So they are avian theropods. So Archaeopteryx was the first, earliest recognized bird, very close in characteristics to the feathered dromaeosaurs. And you can think of Archaeopteryx as an avian theropod, a flying dinosaur. Now, further into the Cenozoic, after the major mass extinction takes out all the non-avian dinosaurs, we see a flourishing of the avian ones, the birds, okay, but also birds that couldn't fly. And some of these were the largest predators of the Cenozoic, very fearsome. As we'll talk about, these theropods are non-avian dinosaurs, if you will. So birds, whether they could fly or not, represent descendants of dinosaurs. Well, I don't want to be biased being a vertebrate organism, so let's talk about pelagic invertebrates. Well, what discussion of Jurassic life would be complete without talking about cephalopods? Specifically the ammonoids, and these are cephalopods or mollusks with the animal extending out of one end. And what is distinctive about cephalopods, specifically Jurassic ammonoids and other Mesozoic ammonoids, is their suture patterns in their shells. Where the internal walls inside the shell meet the actual outside of the shell, it forms a line, and we call that a suture. Some of these suture lines are actually very distinctive, whether they're very smooth suture lines versus very complex crenulated suture lines. And they actually give us some indication of age of the ammonoid. So these wrinkled sutures in ammonoid shells are actually used as index fossils. Okay, here's a cross section of an ammonoid. You can see the internal structure of the different septa walls. In the outside where those walls intersect the shell, you can see the suture lines. Nautiloids are straight-shelled cephalopods, although they can also be coiled. And so there's just different degrees of coiling. Commonly, the straight ones will be straight their entire length, but they can coil at the very end. And then you have ones that are all coiled up altogether. So they're all cephalopods. Some are called ammonoids. Some are called nautiloids. We've seen the straight-shelled cephalopods before, way back into the early Paleozoic. Pelagic vertebrates, critters living above the seafloor that have a spine. Of course, the fish. So in the Jurassic, fish would attain a massive size. Not all fish were like this, but the largest fish that we know of was Leighty. It could have been up to 20 meters long. There are different estimates on its size. This is kind of a maximum estimate, showing some other fish to scale, but Leighty was a massive fish, maybe 50 tons or so. And it just swam very slowly and filtered out food from the water, probably a lot like a whale does today. So this is a ray fin fish, bony fish, the largest of its kind. This is a scuba diver, if you couldn't tell. Well, some more vertebrates. Now, if you were frightened of the dinosaurs, so you didn't want to be on land, and you were frightened of the pterosaurs because they're coming at you from the air, so you go into the water, right? Well, in the water are marine reptiles, remember, and some of them were pretty scary looking. Plesiosaurs were ones that had a robust body and a long neck, small head, big paddle-like limbs. Different types of plesiosaur. This is Cryptocleidos, checking out an ammonoid there. Plesiosaurs and pliosaurs were similar, but there were some distinct differences. One is it didn't have the long neck, so a big, large head, short neck, and had the paddle-like limbs. Different than a plesiosaur in that it had a much shorter neck. Plesiosaur is longer, much larger head than the plesiosaur, much smaller there. So these had different sizes. Leiopleurodon was probably the biggest one of these, the biggest pliosaur. Size estimates vary, maybe around 7 meters. Some earlier estimates were much larger, but they're usually revised downward. 7 meters is still fairly large. Again, you can see the relation with a human here. That's a fairly large marine reptile. So plesiosaurs and pliosaurs. One other important group of marine reptiles include the ichthyosaurs. And we talked about these in the Triassic, where they got their start, and they really diversified in the Jurassic. Very distinctive, streamlined, fish-shaped reptiles. Remember, they're not fish. They have to breathe, so they'd have to go to the surface for air. This would present a problem for them, say giving birth. They would be vulnerable to predators like the pliosaurs. This is Ophthalmosaurus. It's got the big eye socket there. Ophthalmosaurus is right here. It had its origins later in the Jurassic. A whole suite of different ichthyosaurs come on the scene by the end of the Jurassic, and many of them would continue into the Cretaceous until they finally go extinct. Well, last but not least, land plants. This was a time known as the Age of Cycads. So cycads were gymnosperms that really originated in the Triassic but proliferated during the Jurassic and into the Cretaceous. So gymnosperms like cycads, conifers were very abundant. Ginkgos, spore plants were diminishing in abundance but still relevant. But really, land plants were dominated by cycads. And so when you look at these reconstructions, they're the ones that look like pineapple palm tree combinations. That's the typical cycad. A sago palm tree of today, like here at ASU, resembles an ancient cycad.